So that's the quest of the bottleneck, and now you know what this is about bioreactive transport. Bioreactive transport is a little bit different than geochemistry. So it's all kinetics. And I would also disagree that all the geochemical parameters are known. So if you have amorphous spaces, anything that is really exciting for biogeochemists is amorphous, then these coefficients are not well known. And the kinetic coefficients for geochemical reactions is also very shaky. So there are wonderful databases for clear phases. That's easy. But the stuff that is amorphous, that is kinetically controlled, that is difficult, and bugs are always kinetic. Okay, so predicting bioreactive transport, you might say this is a hopeless case in real aquifers if you really want to predict it, not just analyze what you found. You have spatial variability, you have temporal dynamics, you have interactions between transport and reactions, and there's actually, and I will talk about that to some extent, uncertainty in the microbial behavior. Okay? So I would say a unifying theory about the uncertainty and variability of everything is not attainable. So there's some people believe you make the models very, very complex and then you do an uncertainty analysis of that. I think this is not really what we can reach. But often it's not necessary. So if your primary controls are identified and addressed, then you don't have to do an uncertainty analysis of everything, but about the primary controls. So the question is, what the hell are the primary controls? And a microbiological standpoint would be the following. We already started this debate. So I have here kind of a quote, a pseudo quote, because there's no person attached to it. So most chemical transformations of contaminants in groundwater, so I'm a contaminant guy, are catalyzed by microorganisms. We heard a very similar sentence today. And then a microbiologist would say, and that's why we know exactly how they do that. Which organisms, which communities, how do they interact? Nowadays you do this all with genes. What are the exact degradation pathways? What conditions do they need? And sometimes you even get the information how fast they are, even though most microbiologists don't like this question too much. This is what we would like to have from them. A counter standpoint by systems analysis is, and that's again not a real quote, it's more kind of an observation that some people figure out once in a while. So if a chemical transformation yields energy, enough energy, a microbial community catalyzing it will be established sooner or later. So whatever this sooner or later means. So if the conditions are such that you can live on that, you will find some bugs that are doing that. So on the long run, the microbial degradation is then limited by abiotic processes, and for the system behavior, it might be more important to figure out what these abiotic processes are that are controlling it, rather than how exactly the bugs are doing that. So these is what I would call the bottlenecks, and hopefully I have some time to come at the end to cases where it's actually microbial bottleneck. Okay, so one thing is mixing, we heard about that. So the reactants must be at the same location, the same type, and actually the bugs also have to be at that place. And this is the scale of individual pores. We have heard that as well. Physical mixing is typically rather slow, often slower than the actual reaction, even if this is a kinetically bioreaction. So then this can become the dominant control. And any law, and we haven't seen anything of that here, but you see it somewhere else, laws that describe the behavior of ensemble concentrations don't describe mixing. So this is another way of confusion. So often you have ensemble concentration behavior. So for conservative compounds, you think of a million of different realizations and see what the average concentration is doing, how this is spreading. This is not mixing. Now, I was delighted to see that there were many presentations on transverse mixing, because most people don't really make the distinction between transverse and longitudinal. So what direction? And there's another thing, which mechanism? And there's more than mixing by diffusion. Okay, so let's have a brief look at a real site here. This is in Marthalen in Switzerland, where we go with our excursion every year. So you see here features. Difficult to put this into a model. So, and we're now talking about longitudinal mixing, and I will do this very briefly. There's tremendous progress has been made in recent years, and I'm practically have not contributed to that at all the last 15 years. You would have stretching and dilution of line sources. So this is a very old thing that we've done years ago. We started somewhere with your line source, and this is here running ahead somewhere, slowing down. So this is how a line source deforms after a while. You also see concentration variation. Reaction rates, we see something like this. If this is a conservative component, and that is of course somewhere awful. And analysis by people like Tanguy was, it starts off with some ballistic regime, then super diffusive, and finally diffusive. Okay, so my question at this point, and I do this very quickly, is so what type of scenario does this really reflect if we're talking about mixing caused by local scale dispersion? Okay. Now there are potential scenarios for them. One would be a cloud of one reactant surrounded by an ambient solution of the other reactant. Well, there might be cases of this. Another one would be a replacement of a solution containing the first reactant with a solution containing the other. So this would be a longitudinal mixing controlled system. Okay. Now the bacteria must already be present at a sufficient abundance or grow very quickly, and my claim is if you do this with oxygen, they do this quickly enough, so this might be, and we have cases where they're actually around, they have never seen toluene and they were able to degrade toluene in a snap. So that is often not really the case. This is here a bummer, okay? You're not allowed to have sorption so that this diffusion type of mixing is controlling everything, and I would claim that everything of interest has sorption in it. Sorption differences. You're interested in toluene versus oxygen. The toluene is sorbing. The oxygen is not, unless they are gas bubbles, but then it's sorbing in a different way. Okay, so very often the reactants sorb differently. We try to do these type of things in the lab, and we were not able to get it going without sorption in it. So that's, if it's a problem to establish that in a lab, it might also be a problem outside. So because of that, if you say we do it without sorption, it might be an intriguing problem, but of limited practical relevance. Just to shock some people here. So let's have a look here. So longitudinal mixing by sorption. What I mean by that here, a pink solution containing the less sorbing reactant replaces the blue solution containing the more strongly sorbing one. Classical application would be oxygen-controlled biodegradation of petroleum hydrocarbon compounds. They sorb strongly and oxygen not at all. So what's happening, and this is now without the reaction, you see here this overlap where it's getting purple or something like this. This is where the reaction can take place. And we call this chromatographic mixing. So it's a chromatographic effect. You can have this separation, but also as a mixing if you do it in the right order. And this has an advective scaling. So, and on the long run, this will always win, even if the retardation factor is 1.1, which is not a lot. On the long run, this type of mixing will win over dispersive mixing. So you can actually come up with comparably simple laws for these type of reaction fronts. If this also starts to react with very interesting phenomena, but all of these questions of how effective dispersion acts becomes irrelevant if you start to have a little bit of sorption. And that's why I think it's not maybe the major control is then to figure out what are these sorption mechanisms. Okay, so let's have a look at. This is why you use Microsoft, okay? Let's come to this thing here, the Plume-Fringe Concept. So here we have a contaminant source, so this could be a gas station or something like this. And you need oxygen or nitrates or something in the dissolved phase to react with it. This will readily be consumed in the source zone. And then you have this permanent input here. You create a plume. There is no oxygen here in the center because it has been consumed over there. So the only way how you bring it in is from a parallel stream of water from the ambient flow. And at late times, here this invading front has disappeared somewhere over there. So the longitudinal mixing plays no role anymore. It's all controlled by transverse mixing. And it's going into steady state. At steady state, sorption has no effect. It's dropped out. So you're really stuck to dispersive mixing. We've done this really a long time ago in the lab with actually pH indicators. So we had here an alkaline plume in an acidic solution and some pH indicators. So blue is alkaline and red would be acidic. In Tübingen, I was at that time in Stuttgart. In Tübingen, they did this in much smaller, nicer experiments. We were in a hydraulic lab, so we had to do it in 3 meters, so that it's real civil engineering. So the concentration of the reactive species depend on the mixing ratio of the plume-borne water and the ambient water. The mixing is provided by transverse dispersion only, and we came up with a 2D analytical solution under homogeneous conditions. So the plume length was inversely proportional to the apparent transverse dispersivity. So this is velocity over transverse dispersion coefficient. And here you need this mixing ratio, a critical mixing ratio where everything is taking place, an inverse error function. It also scales with the width squared of the source, which is one of the bummers. So you got to know what this effective width is, and this counts a lot. Okay, then we've done a lot of analytical things also for bioreactive transport. So the white line is the outline of a plume if this was an instantaneous reaction. And then the real color here is accounting for biokinetics. And actually you see the DOC is inside, the dissolved oxygen is outside. The reaction product that we're not interested in is produced here along the line. And the biomass really sits along the line where the instantaneous reaction would take place if it was instantaneous. Okay, but it's not getting far away from that, and most of them are sitting here somewhere close to the inlet. These are profiles along this line here. So you see here differences between biokinetic and instantaneous reactions and a conservative mixing ratio. So there's a little bit of a difference if you really start to consider how fast the bugs are, but not really tremendously, and the biomass really sits here at 2 peaks here. And it depends, of course, how you choose your parameters and so forth. Whether this is here 1 meter or 10 centimeters or 2 centimeters. Yes?
When you say the biomass is sitting there, you mean it's immobilized there, or it moves with the velocity?
No, it's growing there, directly at the mixing zone.
So immobilized?
Yes, 99% of the biomass is immobile. I'm going to talk about mobile biomass later on. So these are simulations done by the colleagues at that time in Tübingen. And that was a little bit banana-shaped plume. That's why you see here a vertical offset. And these were measurements. So they measured the biomass. And you see, so where it's darker here, this is at 40 centimeters, 2 peaks measured. Well, also simulated. I mean, it's not perfect, okay? But essentially, a good confirmation. This was a fringe-controlled bioreaction. The only place where the bugs get both, in this case, toluene and oxygen, was at the fringe. And that was then controlled by transverse dispersion. Okay. Now, if you go into a heterogeneous domain, this is getting a little bit more complex. So this is this banana-shaped plume, in this case with fluorescein. And there are some streamlines in there. And then they repeated the experiment with 2 inclusions of higher conductive material. And what you see is, so you don't see the plume anymore. And then it comes out again and comes out again. This is here at the outlet. They measured the concentration profile, the transverse concentration profile. You could fit this here beautifully with a Gaussian distribution. And this one, not so much, does not look like a Gaussian distribution. So what happens here is the following. The high conductivity inclusions squeeze the plume. So there it's narrower, but they come out wider. And the reason is, if you squeeze the plume, the transverse mixing length is smaller. Okay, and the length scales there in the squared. You also have less time because you have a higher velocity. Okay? But that scales only linearly. So if you squeeze this thing at higher velocity, actually you have more mixing. The mixing takes place in the high conductivity inclusions, in these 2D setups. And we've done lots of analysis of that. This is where the mixing takes place. Actually, you can also find in gravel pits, you find the iron precipitates in open framework gravel. There you see iron precipitates. Where somewhere inorganic, inorganic iron, reduced iron and oxygen came together by transverse mixing. Okay, so you have enhancement of mixing there, but not very strong, to be very honest. So mixing controlled steady state reactive plume in a heterogeneous aquifer is computed, of course, a log conductivity field. Again, something that does not look like any real geology. Oxygen outside, contaminant inside, reaction product where they meet. Now the interesting thing is practically everything happens over there. Okay. And why is that so? I don't show the flow net here, but this is a high conductive, there's only one high conductive zone over here. So the water essentially wants to go the path of least resistance, so it's squeezing in this thing here. That's where the oxygen and the contaminant get in close proximity to each other, they make transverse exchange, and they react to the reaction product. The problem is, in a real aquifer, you don't know exactly where these places are. You know these places exist in a heterogeneous aquifer, but it might be here, or it might be over there, or it might be over there. Okay, so this is essentially what we've done in a study a couple of years back. So we did Monte Carlo simulations, so these are our different realizations. With everything was the same, only the hydraulic conductivity field was slightly different. So this is here the source, and this is essentially how large the plumes get. And so some of them are very short and some of them are very big. So you have an extremely uncertain length of the contaminant plume. You can do this analytically too. So this is the original handwriting of Felipe de Barros. If you ever collaborate with him, you get these type of things. He has many colorful pencils. So that's beautiful. I don't go through the equations of that. So we did analytical expressions for that, and essentially it turned out the following. So you have an uncertain spatial variability. And actually the most important part was that you don't know exactly how much water goes through your source zone. So we fixed the size of the source zone, but because of hydraulic conductivity variations, this could be in a high conductive zone or a low conductive zone. Okay? And then the effective width is not the width of the plume, but it's kind of how much discharge goes through the source zone in comparison to how much would go through the source zone if this was homogeneous. So that's the effective width, and the length of the plume scales with the width squared. So that was the most important thing. And essentially you get an uncertain length of the plume here. That's what we derived with cool expressions of Felipe. These were my Monte Carlo simulation. I think this looks pretty good. Unfortunately, so predictable uncertainty, but horribly high. I mean, if you're a consultant and you say, well, you know, the plume might be 3 meters long or 30 meters long, they say, you're nuts. Of course, the good thing is you say, well, if you give us enough money, we do more site investigation. It really pays off, and you can analyze where you should analyze, and it turns out you should know your source zone. Also, some intermediate conclusions here. In steady state plumes, the degradation of contaminants is limited by insufficient mixing of reactants in the transverse directions. The microbial kinetics determine only how long it takes to reach the steady state. I will have more of that. The spatial variability of hydraulic conductivity causes slice enhancement of mixing. I haven't shown this, how strong this is, but we did some analysis of it. And tremendous uncertainty. Not good news. Okay. So then we had a project together with microbiologists from the Helmholtz Center Munich, and the idea was the following. If this is true, they had an observation at the field site where actually the water table changed, or the position of the plume changed. That was the major thing. So the biomass accumulates at the plume fringe. So this is what we said. That's where they're sitting. And now due to some hydrological variation, it might be that the plume moves. Oh fuck, now the guys are sitting up here and the good places are down there. That's not good. Okay? So it would take a while until they start to grow there, and in the meantime they might die off there. So does this control overall degradation? That was essentially the idea. Okay, so we had here a Sandbox experiment. This is more the Tübingen style of thing, so this size here. That was done in Munich. So injection of toluene in a single port, injection of oxygen-saturated water in all other ports, toluene measurements in the outflow, and an oxygen-sensitive stripe. So you can measure this essentially without taking a sample. Okay, it was inoculated with Pseudomonas putida after 16 days. Then 10 days later, this injection port was shifted, and 13 days later, it was shifted back. So that's the experiment. And this is essentially the recovery, so how much toluene is leaving the domain in comparison to how much was injected. A model and measurements. So here's the inoculation. Well, I mean, you see that there are some difficulties here, but the concentration went down here, okay, of the toluene. And then the plume was shifted, and whoops, you got a full recovery again. So everything that was injected was recovered again. Took a while until the bacteria were able to cope with this. Our model said a little bit quicker. And then it was moved back again to the original port, and also a slight enhancement, but then it came down rather quickly. Because there were still old guys sitting around. It used to be good there. It was bad for a while, and then essentially it became the right place again. So after inoculation, you have a recovery of the toluene. So the recovery drops. And after a shift of the plume, it comes back until you establish the bacteria at the right place. And if you shift it back to the original place, the disturbance is shorter. So there, the bugs are actually able to cope for a while with bad conditions. So that's interesting. So they know how to survive hunger periods. So some insights of trying to model these experiments. So the required components in the sense of model components, not the components that Jesus was talking about. In order to get this right, you needed biomass growth, biomass decay, something that's called endogenous respiration. So for a while they can live on internal reserves. Transport of organisms was in there, attachment, detachment, and we needed this crazy maximum density of attached cells as well. So all of that was needed. And we needed also this dormancy. And the dormancy is a mechanism that essentially the bacteria go to bed. So under bad conditions, they fall asleep, and they can be reactivated if they smell coffee and croissant. Okay, so that's more or less, and how they actually do it is kind of a miracle. So then we did, to look, how important is dormancy? Can we do some small experiments on that? So dormant cells, that's the idea, require less so-called maintenance energy. The maintenance energy is essentially how much you have to eat just to keep alive. And if you're sleeping, you don't have such a high maintenance energy, and the bugs, they're really shutting off lots of things so that they can minimize that. There's a rapid reactivation after the end of the hunger periods. And so that is essentially a way how bacteria can cope with dynamic environmental conditions. What this means from a system dynamics or system behavior types of perspective is you need to establish the community once, and then they can be reactivated rather quickly. So that changes the rules a little bit. This is our Hunger Games in mini columns, 1.6 centimeters. So this was a continuous injection. Here was short hunger phase, and here a long hunger phase of 130 days. Okay, what happens after continuous injection? Sometime here the toluene drops down. Oxygen was also introduced, also drops down. Model and measurements, and okay, that's kind of boring. So now short hunger phases, you see, whoops, a spike. The model is over-predicting this a little bit, but you see the toluene came up here after 8 days of hunger, okay, and then here 21 days. Now, oxygen was essentially introduced all the time, and at the time when there was no toluene introduced, you had a breakthrough of the oxygen. But the most interesting thing was this year. Even after 130 days of hunger, the bacteria only took a few hours to be fully reactivated. That's cool. That's what I meant. If you're primitive, well, you may figure this out, so it's much easier to date if you're primitive. So then the same thing holds here for these bacteria. So they can shut down things. We also looked at bacteria. So this is our bacteria attached to the surface. Actually, in these hunger phases, you don't see large changes in the numbers. They started to become a little bit smaller. And these are mobile bacteria. Okay? So in these hunger phases, whoops, no mobile bacteria in the outlet. There was some measurement error here. As soon as they got food, they would release cells. This is what is called growth-mediated transport. So if there are good conditions to grow, but all the places are already taken, they release the daughter cells. That's a mechanism that some bacteria have, like this one. So the attached cells hardly disappear in the hunger phases, and the mobile cells occur only in the growth phases. Okay, so next set of conclusions here, the microbial kinetics. So Dominic Eckert, who did the model, said, well, this is horribly complicated. We have to include all of these processes, so growth-mediated transport and dormancy and blah, 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 blah. Well, actually, for the overall system behavior, it may be not that relevant for these type of systems. So a microbial community that was established in the past can readily be reactivated in the future. So that's essentially the overall behavior. So at the first occurrence of a contaminant, biomass really, the growth of the biomass controls the degradation, but until then some abiotic processes become limiting, but the reactivation is much, much quicker. Okay, so here's a different setup. So this was all transverse mixing, and now we have here a tale of two valleys. Actually, this is close to Tübingen. There should be the Wurmling and Chippel up there. So it's a fate of nitrate in a 2D vertical cross-section connecting two valleys. This is the Neckar Valley. There's a gravel aquifer here with low natural organic matter, and it's overlain by alluvial fines. And on the other side, we have the Ammer Valley. These are floodplain sediments over there, and they have very high natural organic matter. The hill slopes and the hills are made of Upper Triassic mudstones, so they contain gypsum. This is an oxidizing environment. And the flow, the groundwater divide is on this side here of the hill. It's not up there. And there is input of nitrate by agriculture. So this is a model thingy we're currently trying to figure out how it really looks like. So what's happening on this side of the valley is if this nitrate-rich water hits at least in the model, hits these sediments here that are full of natural organic matter, denitrification is taking place. So this is one type of mechanism what controls the fate of nitrate. And on the other side, it's completely different. So here a nitrate plume is showing up at the bottom of the aquifer, and it has to mix with dissolved organic carbon that comes from the top. This one here is controlled by transverse dispersion. Okay, in this case in the vertical direction. And that was what I discussed in the previous slides. This one requires a 2D model. This here is controlled by the electron donor release in these floodplain sediments. And that may be modeled by the type of things that I talked about in my lecture. So it's not that I've given up on transverse mixing, it's only that I say you have to see under which conditions this is the dominant process and under which condition it's something else. So the control of interface mass transfer. So now we're looking at reactions between immobile and mobile phases in the plume core or at an invading front. So this could be also other things like dissolution of naples. That's an immobile phase typically. Release of electron donors like NOM, DOC from NOM, might be ferrous iron or sulfide from pyrite, it might be biotite, so things like this. You could also have systems where you're looking at a release of an electron acceptor. So if you have iron 3 coatings, then this is releasing iron 3, and this might be good for oxidation of certain compounds. So sulfate can be an electron acceptor for toluene degradation. So in this system, the macroscopic dispersive mixing is not so relevant. The relevant thing is how do this stuff here of the immobile phase makes it into the mobile phase. Okay, so we had this thing here before. So nitrate and oxygen introduced by recharge. DOC released from organic-rich sediments. Decisive is now the question, how long has a water parser seen those organic-rich materials? So this is what I've been talking about before, and I've shown this one, the type of thinking that we had with this cumulative relative reactivity, some mapping approach, trying to get these pictures here. So I've done that. Actually, what we what we're currently at, Jan Fleckenstein is involved in this. We have a collaborative research center, a catchment scale, and this is called catchments as reactors. And one part of it is we try to come up with a catchment scale stochastic modeling framework. And catchment is a smaller catchment. Okay? And the idea is the following. The idea is to classify the land surface with combinations of land use and soil types. Then use complicated 1D land surface models for each class, because there you have all kinds of feedbacks, and all these funny things that I've been talking about is not valid. Okay, so the plants are affecting the water flow, and this is actually having to do with how much nutrients are around, and everything is mingled up. But there's not necessarily a need to do this in 3D. Okay, so these are 1D models. Then a 3D classification of subsurface units, and with some internal heterogeneity and uncertainty, a 3D groundwater flow and particle tracker, and then trying to do this reactive transport with this funny cumulative relative reactivity. So there are components in that where I would say it's mechanistic, like these land surface model, and we try to do things in 3D, and we try to bring at least some of the reactions right into the system. And yet we try to be as efficient as possible so that we reduce some of the complexity in order to be able to do some ensemble calculations. So whatever this exactly is here, there are lots of integrals with probabilities in there, so you have to do many of these simulations, and we're currently working on that. Okay, so now the last thing is, I've told now all the time the bugs are doing all the job, but how they're doing I'm not interested in. Is this really always the case? And the answer is no. And I'm also writing proposals where it's all about what the bugs are doing. So these examples were based on the assumption that the solute transformations facilitate microbial growth. So it's good food for the bugs. Contaminant hydrogeologists are extremely biased because we love contaminant plumes. And this means we have high concentration of the pollutants, and this is like a stacked buffet for specialized bacteria. If you're interested in what toluene degraders are doing, go to a gas station. It's a wonderful place for them. Okay? And that's why all the toluene is there, so now you run into other problems. Okay? Also, most microbiologists love to study turnover under growth conditions because it's so damn difficult to do it if they're not growing. Okay? But under growth conditions, well, you have to ask the question, how often do you really have that they're tremendously growing? That's often not the case. Okay? So often natural turnover, if you're not in a contaminant plume, if you're talking about critical zone processes, I hate this word. Where's Kamini? I hate this word critical zone. I think it's stupid. Okay? So the biogeochemistry, natural turnover, this is often at the energetic limit. There's hardly anything that you can chew on, but they still do it. And then it's much more interesting to know how they're doing it. Microbial dynamics are rate limiting when a new community must be established. So this is what I tried to explain before, this first time exposure to a reactant, and particularly if there's little energy to be gained by the reaction. In comparison then, a reactivation of a dormant bacterium, that is a quick thing. Now, here's something that I find totally intriguing. So what if there is no obvious benefit for an organism to perform a reaction that you're interested in? This happens more often than you think. Okay? So, and this can also happen that there is something missing. So for a complete dechlorination, you need to have vitamin B12 or similar compounds. And the only organism that is able to do the complete reductive dechlorination of TCE, so from vinyl chloride to ethene, is not able to produce vitamin B12. It needs a body that is doing that for it. Why the fuck does the body do that if there's no direct gain in that? So these are systems that are, let's say, more intriguing from a microbiological standpoint of view. If you want to do something where the microbiology is really determining the system behavior. Okay, one thing is micropollutant degradation. So very, very fashionable currently. Pharmaceuticals, artificial sweeteners, personal care products, all of these things are called micropollutants. Nowadays they call them emerging pollutants. The important thing is micro means nano, so that you find them in nanogram per liter concentrations in the environment. People are very much concerned about it. There is no way that I can imagine, at least, that these organisms can live on degrading 2 nanogram per liter of isopropene. There's not enough energy in it. They do it, sometimes they do it, okay? So why do they sometimes degrade those compounds and sometimes they do not degrade those compounds? Okay, so there is something, and you don't see big slides with results because we're thinking about this. So some micropollutants are actually better degraded under conditions when there is no good food around. So they are able to degrade the micropollutants if they don't get good food. That's interesting. Okay. So a potential mechanism is that the organisms activate all pathways that they have when they are hungry. Okay, so if they get good food, they activate this one pathway. They get toluene, great. They do toluene degradation. Why should they activate pathways to do other things? This is a little bit like spoiled kids. So they're willing to eat vegetables under conditions when there's definitely no ice cream available. Okay, so this is how you can imagine this. And they even do this with pathways where there is no food around there. So it's kind of like a panic reaction. Oh, let's do everything. I don't see good food, let's do everything before I die. Okay, so that's the type of thinking. So just to be ready if anything is passing by that they can do that. That is an interesting mechanism and might be very important, and there are people working on that, actually how to create hunger periods that you get a good turnover of micropollutants. There's an alternative mechanism that is somewhat better understood, so that's the degradation of micropollutants if they are structurally similar substrates from which they actually can gain energy. This is a classical co-metabolism. And that has been used in the past, in the 1990s, a lot to stimulate aerobic degradation of tetrachloroethene by adding actually toluene. So you add a different contaminant. So aromatic compounds, if you don't like that, you could also take isoprene. So these are the primary substrates, and the enzymes that do the degradation of the primary substrates, by fortune, can also degrade the TCE. So that's a mechanism that might work out. Altogether, a suitable modeling framework that is able to cover this type of mechanism and the other one, that's an absolute research topic. How this is actually, what are the rules that are doing that, and how can you bring this into equations? This is a very open field. So I'm coming to my end, presumably wise word of an old man. I feel an old man, even though Rien van Genuchten is older than me. So the behavior of contaminants in the environment, that's not pure chemistry, even though some people say, oh, it's all about transformations. It's not pure microbiology, even though the bugs are doing the job. And it's also not pure physics, even though we're totally fascinated by transport. So it's actually, it is the interactions, the interplay between those different processes, and it's kind of your role to know enough of the other fields to figure out what you need to know to understand this system. Now, another personal advice of an old geezer. So you should perform I would say, a preliminary system analysis of, if you're interested in reactive transport, in each individual application. So don't think about what was the right thing the last time. Think about what is the right thing this time. If it's exactly the same, it's a little bit boring. Typically, you do something else. So what is controlling the system? Think about it. Talk to the people who don't love equations about it. I mean, I love equations. The least problem is to find equations, to figure out what the microbiologists, the geochemists, and all the other people think what's going on. That's the difficult thing. And they always think that I want to talk. They're totally astonished that I say, okay, tell me what you think, and I ask critical questions, as you may imagine. Is this consistent what you think? And then if we come up with a consistent story, okay, then I'll write down the equations. Try to identify the bottleneck in each specific situation. Okay, So you don't need to have a tool that is able to do everything. You need to have a tool that is good for your specific situation. And then you have to be accurate in predicting the controlling factor. And actually, you're allowed to be sloppy in the non-controlling factors. This is a cool thing. You may introduce simplification of the non-controlling factors. You may have a scheme that has tremendous numerical dispersion if the dispersion is irrelevant. And I've done this a lot, but I knew exactly when I did it, and I knew when I'm not allowed to do this. And this is my personal thing here. Mind your professor's personal pet problem. So this is the YP4. And what I mean by that is be careful that you don't do the thing that was exciting in the dissertation of your PhD advisor. Try to find something that is now exciting. Don't follow just the tracks. That's boring. So the interesting thing is to essentially prove that your advisor was wrong because he has forgotten something and something else in this application is important, rather than just redigesting things that have been around for many years. Yes?
How would you, maybe can you comment on what you think, how the biomass would impact the flow field and the transport in the mixing?
That has been studied. So the question was essentially about bioclogging. That has been studied. And so I worked a lot with Christian Griebler at the Helmholtz Center Munich. And he told me, and I have to believe him, that this is vastly overrated. So Martin Tullner did an experiment to show that. But he had a system where the substrate was glucose. Come on, how much glucose do you have out there? And so the bacteria were then producing lots of extracellular EPS. What is this? Extracellular polymeric substances. And that was just goo that filled everything up. Okay, and then when I started this collaboration with Christian, he said, yeah, Martin and his experiment, he has no clue of microbiology. So essentially, he showed me pictures of what so-called biofilms look like. So what do you think how a biofilm looks like?
It cells completely.
That's okay. So how do you have any idea how bacteria how they form in the subsurface? Okay, so I thought that this would be films, okay, because it's biofilm. And that's what you have in sewage treatment plants. And then he showed me pictures. So this was, in reality, the grain was this size, so blown up like this. Okay? And there was here a little colony. There was a little colony. There was a little colony. And there was a little colony. A colony is maybe, 20 cells or something like this. So in a eutrophic aquifer, there's hardly any biomass in there. And what we did not understand, so there's no way that this is having a huge impact on the flow field. What I still find completely puzzling, if there is so little of these bugs, why don't they grow up to higher biomasses if conditions are good? And they don't do. So there's this funny carrying capacity, we have not understood it what it is. So you would expect that they grow until everything is filled up, and we don't know why that is the case. So I assume that under most conditions, what I learned from actually groundwater microbiologists, so that's not my statement, that this bioclogging is overrated. However, if you are in a system where you have denitrification or methanogenesis, you can have gas clogging. So you produce nitrogen gas all the time, and as soon as the partial pressure, the sum of the partial pressures is higher than the hydrostatic pressure, you start to create bubbles. And the bubbles will fill up the large pores the first. So maybe more of the clogging that you see has to do with gas formation, particularly in systems where there's lots of food around. Yes, sir?
There is no universal solution, and you've said this.
There is no universal.
Clogging does occur in many places. Gas solution, you have to be very shallow. In the lab, you will have a solution. At 20 meters
Yes, but the bioclogging, the typical systems are in technical systems. So in sand filters, in sewage treatment plants, they have huge problems with bioclogging. But this is a superb buffet. All the shit that is in there, and it's really shit. So this is wonderful food. And then they form this bio, actually it's called Schmutzfilm, so it's a German word, on top. And you have to remove this by opposing flow. But I'm talking about normal aquifers. You don't have this. You don't have that much shit in the aquifer. Okay. So.
I just wanted to say that also in petroleum reservoirs, I guess we have to consider as biofilm.
Yeah.
Because we have always this residual oil saturation, and then we inject nitrate and sulfate, and always, I guess we have this diffusion of organic matter from the residual oil saturation, and we have always that residual oil saturation, and it's quite significant. So I think maybe it doesn't clot, but it takes some of porosity, so it affects permeability and also PC.
In all, some very often it's with biocides.
Biocide doesn't help, so they inject nitrate.
Oh well, that would be to actually let them grow. Yeah. So I'm not a specialist in that, but there are people working on that. Essentially, in these systems where the bugs sit, and there are actually bacteria that directly sit on the petroleum, and they suck out the electrons directly out of the petroleum, and they get the electron acceptors from the liquid phase. And they produce their own little surfactants, and I guess they really have to do a lot of stuff because it's rather poisonous to be there. So this EPS production depends very much on what type of environment you're in. But you will hear something about that most likely next week when some people will tell you that microbiology is the most important thing that you can think of, and Philip van Capellen will tell you everything is bioenergetics. I already know that. Yeah?
I'm glad that you talk about the ensemble of concentrators.
Yes.
But please state also the fact that the ensemble concentration is really tricky because it's giving you, especially about mixing, forget it. Spreading something, but state loud that it is because we are when you play with the ensemble, we are mixing the physical phenomena with uncertainty.
So what I meant by this is, okay, so there are people who are crazy about laws for conservative transport, let's say anomalous transport, and there are different formulations of doing that, and they say, it's wonderful, it describes the ensemble concentration. It would be the same thing as looking in a very, for a conservative compound, a very white plume, very wide plume, and you're looking at the cross-sectional average of that. So for mixing, this is not relevant. For spreading, it is very relevant. And for uncertainty analysis, it can also be relevant. So if your regulator says, let's say in Germany, we have the protection zone, 50 days of travel time. And you have uncertainty. And then you can essentially say, well, the ensemble concentration, you can relate this somehow to an arrival time probability. And you go, well, you know, if you want to have those 50 days, here it's to 90% sure, and here it's to 99%, and there's only 50%. So I don't have any problem with people doing these type of things if they know what they're doing. And in the early times, there were big errors made that the macro dispersion coefficient were named mixing coefficient. It was completely wrong. And I think it's for students very, very confusing that there are all kinds of dispersion coefficients and they have a different physical meaning. So one is essentially describing the spread of an ensemble plume, and the other one is describing actual mixing, and then a third one is describing pore scale processes. And I love to use those for transverse things. It's the uncertainty of plume meandering. And that can be very, very, very confusing. The problem is that dispersion is confusing. So you deal with aspects of heterogeneous porous media or fractured porous media, and you got to be very clear when you write things down which aspects are you talking about if you use now this coefficient and then you ask the right people whether you use the right term for the right process. And not all, I've somewhere found something on the web